This lesson will cover Big Idea 2, Standard 2, and our topic is periodic trends. So different elements on the periodic table have similar properties based on their location. Elements that have similar properties will be found in similar areas on the periodic table. So first, there are three types of elements found on the periodic table. The first are called the metalloids. We'll talk more about the properties of each of these groups in Standard 3. You can find the metalloids on what we call the staircase. On my periodic table, I colored the metalloids in pink. So if you notice, there is like a dark black line that goes down your periodic table. That kind of looks like a staircase. So every element, except aluminum, every element that touches the staircase is considered a metalloid, except aluminum. So elements on the staircase are the metalloids. The nonmetals are elements to the right of the staircase plus hydrogen. Metals are the elements to the left of this staircase. So again, looking at our periodic table, I highlighted the nonmetals in blue, but any element to the right of the staircase plus hydrogen would be nonmetals. Everything to the left, everything else on the periodic table that I did not color would be a metal. Let's say you were asked to predict if the following elements are metals, nonmetals, or metalloids. And you were asked to predict based on their electron configuration. So probably the easiest way to do this problem is just to count the number of electrons and figure out which element it is. Once we know what element it is, we can predict what type of element it is based on its location on the periodic table. So A, 2, 4, 9 electrons. Atomic number 9 is fluorine. Fluorine is to the right of the staircase. So this would be a nonmetal. B, 2, 4, 10, 11. An atom with 11 electrons would be sodium. Sodium is to the left of the staircase. Metals are found to the left of the staircase. So B would be a metal. C, 2, 4, 10, 12, 14. If I look up atomic number 14, this one is silicon, silicon, atomic number 14. It is on the staircase, so it would be a metalloid. So again, based on an element's location on the periodic table, we can tell if it is a metal, nonmetal, or metalloid. The next important periodic trend to know is that elements with the same number of valence electrons react in similar ways and have similar properties. So let's do 2 examples for this. Which of the following would be most similar to calcium? And our options were potassium, argon, magnesium, or carbon. So the key to this problem is that elements that are most similar have the same number of valence electrons. So calcium is in group 2A. That means it has 2 valence electrons. Any element with 2 valence electrons would be similar. And look, magnesium is also in group 2. So our best answer would be C, because both magnesium and calcium have 2 valence electrons. You could also be asked a problem like this if you were given electron configurations. Which of the following would be most similar to an element with the electron configuration one s2, 2s2, 2p, let's do 4. And let's say your options were A, nitrogen, B, phosphorus, C, sulfur, D, chlorine. So there are a few ways that you can approach this problem, and I'll go over both of those. Remember we said valence electrons are in the outermost energy level. So I have the first energy level and the second energy level. In the second energy level, I have 6 valence electrons. So we just need to figure out which element has 6 valence electrons. Which element is in column 6? And I see sulfur. The other way that you can do this is figure out which element you're given in the problem by counting the electrons. 2, 4, 8. An atom with 8 electrons would be oxygen. And now we can see oxygen and sulfur are both in column 6. Elements with the same number of valence electrons are the most similar. Last trend for today is reactivity. And what we need to know about reactivity is reactivity of metals increases down a group reactivity of metals decreases across a period. So let's say we have our periodic table and it looks something kind of like this. Reactivity increases down a group. So as we go down, reactivity increases. It decreases as we go across. So this is my trend for reactivity. The most reactive elements will be down and to the left. The least reactive elements will be to the up and to the right. And this is for metals specifically. So let's say we were given a few electron configurations. Which of the following is the most reactive? Well, let's start with one before. We'll do one without electron configurations, and we'll do one with electron configurations. Let's say you were given rubidium, strontium, and potassium, and you were asked which one is most reactive. So whichever metal is farthest down and to the left would be the most reactive. So I have potassium, rubidium, and strontium. Reactivity increases this way. Rubidium is the farthest down. Rubidium is farther down than calcium. Rubidium is farther down than potassium. That means rubidium is more reactive than potassium. Rubidium is to the left of strontium. Whichever element is the farthest down and to the left would be the most reactive. So rubidium would be the most reactive. Let's look at another problem. Let's say you were given electron configurations. So again, easiest way to probably do this is to figure out what the elements are first by counting their electrons. 2, 4, 10, 11. Atomic number 11 is sodium. 2, 3. Atomic number 3 is lithium. 2, 4, 10, 12, 18, 19. Atomic number 19 is potassium. So we're going to compare sodium, lithium, and potassium. Reactivity increases as we go down a group. So sodium is more reactive than lithium. Potassium is more reactive than sodium. So our answer would be C, potassium. Last thing to talk about. We're going to talk about those noble gases again. Noble gases are inert or unreactive. So we saw the reactivity increase down into the left. When we're talking about noble gases are never reactive. The reason why, it is because noble gases already have a full outer shell of valence electrons. So let's look at something like fluorine versus neon. Fluorine has an electron configuration of 1s2, 2s2, 2p5. Neon would be 1s2, 2s2, 2p6. Again, valence electrons are in the outermost energy level. So fluorine has 7 valence electrons, whereas neon has 8 valence electrons. So the reason that fluorine ionizes, the reason that fluorine is going to gain 1 electron is because it wants to have 8. So fluorine reacts by gaining 1 electron. So it has 8 valence electrons. Neon is unreactive because it already has 8 valence electrons. So what happens when fluorine reacts is it gains an electron. It is going to react with another element in order to gain an electron. Neon, on the other hand, is not going to react with any other element because it already has the preferred amount. Neon doesn't want to gain any electrons, neon doesn't want to lose any electrons, so it's not going to react with anything. So just keep that in mind. Noble gases are unreactive because they already have the preferred number of valence electrons.